Thank you, Professor Chen, for your introduction. First, I would like to thank Anchorage Director Zhou inviting me to join this conference. Today, I'm talking about metamaterial. To be exact, we like to apply metamaterials for seismic design. Also, to be exact, again, for seismic isolation. First, I would like to thank the strong support by NSF, Department of Energy, Anchorage, and also UT Austin facilities. I want to especially point out Professor Stokey and Professor Chen give me very strong support in the past 10 years. So we have some result to report today. All those are the collaborators in the past 10 years. First, I would like to tell you about the idea why we want to use metamaterial for seismic design. And then I will show you the theory. Once we have the theory, I talked to the Department of Energy sponsor. They said, do you have any feasibility study? And then I talked to Professor Chen. I said, hey, can we perform shake table test here? And I got very strong support by him. And after we did the feasibility study very successfully, we know for design we need to have sensitivity analysis to quantify the important variables. After that, I talked to the sponsor again, DOE. They give us very strong support to do the real experiments. And later, they even asked me to apply our metamaterial to the real small modular reactors. And today, our focus will be current state. What's happened up to now? Okay. Before my conclusions. All of us know seismic values of structures and conventional isolation system. There are two issues. The first one is lack of isolation in vertical direction. Second one is they are prone to rocking under vibration. Therefore, we got this idea. When we read the paper published in Nature Materials, this paper, in this paper it's mentioned those are the scientists working in physics, to be exact, as solid-state physics researchers. They developed metamaterial. At that time, they call it phononic crystal, right at the beginning, more than 15 years ago. And later, people call it periodic metamaterials. Lately, everybody call it metamaterial. Therefore, all those three terms are the same. What is metamaterials? They are novel composite, okay, come from solid-state physics researchers. They developed. A metamaterial is a material, okay, having a property that is not found in nature. They are made from assembly of multiple elements. And the materials are usually arranged in repeating pattern. They derive their properties not from the property of base material, but from the newly designed structures. That's the key point. And their shape, geometry, size, orientation, and arrangement will give them their smart properties. With these smart properties, the incoming wave can be bucking or reflecting. Just for example, mentioned in this paper, if the frequency of the incoming wave is located in the frequency band gap of the metamaterial we designed. And then this incoming wave will be reflected back. After we get this concept, we thought we should use this metamaterial as our foundation. And then on the top, we can build our structure. By doing so, the seismic wave, when they come, it will be reflected. In contrast, if the frequency of the incoming wave is outside the frequency band gap, the wave will be passing through. Of course, for this case, the superstructure sitting on this metamaterial will be shaking, just like conventional foundation. That's the major idea. And then, when we are talking about phononic crystals, we have 1D, 2D, and 3D. As you can see, for this 1D metamaterials, this is a one unit cell that is made of concrete, rubber as one unit cell. And then we repeat another unit cell and repeat another unit cell in one direction. We call it 1D. If we have a unit cell, as you can see, like this one, we'll repeat in X and Y directions. We call it 2D. And then, similarly, if we have a unit cell, like this one, we repeat this one in all X, Y, Z directions. It's 3D, phononic crystal or metamaterial. For this 1D metamaterials, as you can see, once we solve the wave equation, we will be able to obtain the frequency band gap from here to here. Okay. Frequency versus wave vector. This will only show you a little bit about frequency band gap. Now I want to show you this slide, especially I just mentioned to you, if the frequency of the incoming wave is located in the frequency band gap of metamaterial we designed, this incoming wave will be reflected back. It cannot pass through. In contrast, if the frequency of the incoming wave is outside the frequency band gap, this wave will be passing through. This is a we designed metamaterial. This is very, very interesting. From this idea, we think we should apply metamaterial to seismic isolation. And then now I want to show you the theory. As you can see from the wave equation, we will be able to find a dispersion relationship. From dispersion relationship, we can find the frequency band gap. The most important is frequency band gap. The method to solve this wave equation, there are several methods, even more. Here I just list the two, but basically the researcher working in this area now around the world very likely to use finite element method. The theory is this is the wave equation. We have periodic metamaterial, so we have periodic boundary condition. This boundary condition substitute into this wave equation, we get eigenvalue problem. When we solve this eigenvalue problem, we obtain those solutions. In a certain range, no solution, this is the frequency band gap. This is the frequency band gap. For this case, starting from here to here. And then we also did a numerical study for 1D metamaterial. This is the metamaterial, concrete, rubber, concrete, and this is a superstructure. We make it become an equivalent structure. As you can see, after we perform analysis, we plot the FRF versus frequency relationship. This FRF is defined by the solid state physics researchers. Frequency response function, they call FRF, defined as 20 log data out divided by data in. Data out, for our case, is the top response. Data in is the bottom input. If this ratio is equal to 10%, that means 90% vibration reduction. Okay, this FRF will be equal to minus 20. Minus 20. As you can see, for this case, minus 20 somewhere here. So we have a very wide range of frequency band gap. See, those are frequency band gap. Even though you can see we may have some pass band somewhere here. So keep in mind FRF is the key variables, frequency response function. For 3D metamaterials, we have two types. We can also find the frequency band gaps. And then we did the feasibility study with the strong support by Professor Chen. We did the shake table test here, right here. This is a 1D metamaterials. As you can see, this is a steel frame sitting on the metamaterial foundation. This is the same steel frame sitting on the shake table. You can see specimen B as this one. The acceleration, the response at the top of the structure almost equal to 0. In contrast, for this specimen A, the vibration is much, much higher. And then we are quite confident now. We already did the test. We want to find out which variable control the design for the metamaterial. We did the so-called sensitivity analysis. We go by Sobel indices. As you can see, what we found is that density ratio played the most significant role. Density. As I mentioned to you a while ago, the base material, we have concrete as one base material, rubber as another base material. When we combine together, become a unicell. That is so-called metamaterial. Okay. The density of these two base materials are the most important to find the starting frequency of the first frequency band gap. Similarly, for the width of the frequency band gap, the width, we find the most important variable as the height ratio of the two base materials. And then we did the free field test with the strong support by Professor Stokey. We did 2D metamaterial foundation. As you can see, we just cut this part, put here, and then at the top steel frame. And this is steel frame direct sit on a concrete foundation. This one also sit on a concrete foundation using Professor Stokey's shaker to shake it. As you can see, for 2D, with the periodic metamaterial foundation, the vibration reduced to about 50%. Similarly, for 3D metamaterial foundation, we just cut a strip here, this strip, put to here. And this one is RC column. At the top of both. This is an RC column, this is a metamaterial column representing 3D foundation. At the top is a steel member. As you can see, the response right at the top of the structure. For this case, with metamaterial foundation, the vibration is so small, reduced more than 90% when compared with conventional RC foundation. And then Department of Energy asked me, can you apply metamaterial foundation to small module reactor? Which we did. Department of Energy even asked a new scale to provide all the design detail to us. So we get all the detailed design for the small module reactor. The length about 100 meters, height 40 meters. We first did the model analysis to find the natural frequency, but to use our shake table 5 meter by 5 meter, here in this lab, we need to scale down. The scale is 1 to 22, scale down. This is our scale down the design. There are 1D metamaterial foundations. We design like this one, as you can see. Rubber, concrete, and this is the superstructure become an equivalent layer. And when we did the analysis, as you can see, subjected to S wave, P wave, the yellow region stands for the frequency band gap. And FRF versus frequency, you can see 0 is here, minus 20 somewhere here. Actually, we can cover a very wide range of the frequency for our frequency band gap. And then we did the shake table test. As you can see, this is RC foundation. This is a metamaterial foundations. This is a test setup. We first did the frequency sweeping test, as you can see in horizontal direction, vertical direction, and torsion mode. These two are very good. In vertical direction, we still find the vibration reduction. And this shows seismic test, the result. The pink curve is the roof of the superstructure with our metamaterial foundations, pink curve. The black curve is the shake table input. The light blue is the top of the periodic foundation. Okay. As you can see, the y-axis is the acceleration. The earthquake we use Bishop, Gilroy, and Oroville. When we transform the time history to frequency domain, as you can see, the pink curve, the amplitude become very small, very small. We know, metamaterial foundation, okay, isolate all the incoming waves for all these 3 seismograms. And this shows the displacement comparison with the RC foundation and metamaterial foundations. Continue, we also did this harmonic test. This shows the comparisons. And then, after the test, we also did the final element simulation to simulate in the test. Our simulated result compared with test result, they are very close actually. So we know we can actually use final element to perform the analysis, especially for the entire structure, including metamaterial foundation and superstructures. And this shows the horizontal direction, torsional mode, vertical direction for all kinds of vibrations. The test compared with finite element simulation, they are quite close. And after that, I showed the Professor Stokey, and he said, up to now, you only consider metamaterial foundation. How about if we put this metamaterial foundation, okay, in the vertical direction and embed into the ground to make it become a combined metamaterial barrier and the metamaterial foundation, the isolation even better. And we got the support from NSF. When we perform the test, if the vibrator is outside somewhere here, we call passive testing. If we put the vibrator on the top of the structure, we call it active testing. Okay, now I just want to show you some results due to the time restraint. This is how we find the FRF. As you can see, this is a metamaterial foundation supporting a steel frame. This is a metamaterial barrier. And the shaker is here. Barrier and foundation. This shows how we get the FRF. As you can see, when we combine metamaterial barrier and metamaterial foundation, FRF even much, much lower in all three vibrations: vertical excitation, horizontal cross line, horizontal inline. So we know metamaterial for seismic isolation works. But now the remaining problem is when we design the metamaterial, okay, we will have frequency band gap. But the frequency band gap, okay, in general, cannot cover the entire frequency of all kinds of seismograms. Sometimes we do a passband. So, due to this reason, our next step is to develop so-called tunable or adjustable metamaterials. What's that mean? Actually, this tunable or metamaterial or adjustable metamaterial, a lot of funding agencies call for proposal, including Department of Defense and also NASA. NASA also interested in this one, invited me to give this talk actually. But I did not show any here. So our goal is to develop tunable metamaterial. How? The rubber we want to replace with MRE. When we use MRE to replace rubber, this MRE we can develop by ourselves using all these ingredients to develop MRE. MRE is magneto-rheological elastomers. Okay. If we increase the magnetic field, the stress strain curve will be changed. The Young's modulus will be changed. Therefore, the frequency band gap will be changed. This is our test in our lab. We increase the magnetic field by using electrical current. This is the current state. As you can see the result, the stress strain curve, when we increased the magnetic field, the stress strain curve going up. Therefore, the Young's modulus also increased. For all three types of MRE we developed up to now. As you can see here, the Young's modulus versus magnetic field. When we increase the magnetic field, Young's modulus will be also increasing. That will make the frequency band gap changed. And further, we did a small scale 3D finite element simulation, use a 2-story building. The bottom is our MRE and the concrete layers to simulate metamaterial foundations. Those are the three types we used. And we can increase the magnetic field from actually 0, as you can see right here, 0 to 50 MT, micro Tesla, and up to 750. As you can see, the lowest FRF will be shifting with changing the magnetic field, shifting. In other words, from what I'm showing you, tunable metamaterial can be developed. After we develop, the next step, we need a control, okay? Control. That means if earthquake coming, the frequency, we don't know. But right on the metamaterial foundation, we put an accelerometer. From the accelerometer, get the measurement, transform the time history direct into frequency bandgap. Once we get to know the frequency, incoming frequency, we will adjust our magnetic field to have the frequency for covering the frequency of the incoming seismic wave. But now what I'm saying is only one method to develop tunable metamaterial. What we found in some other field, they developed tunable metamaterial using different methods. Some, they develop so-called negative honeycomb unit cell, just for example. So, up to now, I already presented all the current state. And I can make the conclusion. When you see the figures in my conclusion, you may agree with me. Again, actually, our research started from science. We applied to engineering. And we also go from theory to analysis to experiments. The frequency bandgap is existing from the theory, analysis, and experiments. And the frequency of the incoming vibration is located in frequency bandgap. The wave will be reflected back. This is we already proved through all kinds of studies, experiments, several sets of tests already. And also we did a lot of analysis. As I mentioned to you a while ago, we actually applied this concept to small modular reactors. It's working, it's working. And NASA invited me to give this similar talk. I did a metamaterial, okay, for space structure, to be exact, for satellite. And that was also successful. Now, I can say currently the most important is how to develop tunable metamaterial for vibration isolation is a hot topic. Thank you very much for your attention.